So we will start today with a new chapter, okay, which is chapter 3, mechanical properties of materials. So I think if you have already taken a mechanics of materials course, you will be familiar with the majority of ideas in this chapter, okay? So first we will consider the stress-strain relationships, how to measure hardness, the effect of temperature on properties of the material. We will go then over fluid properties and viscoelastic behavior of polymers. So this is in summary the outline of this chapter. Now, mechanical properties are very important to determine the material behavior when subjected to mechanical stress. And you know that in manufacturing, it's very important to know the mechanical properties because we want to change the geometry or change the properties of a certain product to end up with a final product. Okay, so it's essential to know what are the properties of the object before we decide what are the manufacturing processes that can be done to obtain the final product we want. So we should know about the elasticity of the object, its ductility, its hardness, and various other measures. So we have also a main problem that in general, the mechanical properties that are desired to the designer, such as high strengths, will usually make manufacturing more difficult because if you have a certain material with high strengths, it will not be easy to deform it because when you want to do deformation, you need to apply certain forces that will deform your body. So if it has a very high strength, you will need to apply very high loads to do deformation. On the other hand, okay, so high strength has a disadvantage whenever doing the manufacturing process, but at the end, your final product, it's important to have high strength. So you should always have, for example, it will depend on the application, okay? It will depend on the application to do a compromise between the two, between the mechanical properties that are needed for the designer and the mechanical properties required to do the manufacturing process. Now, concerning the stress-strain relationships, we have three types of static stresses to which materials can be subjected. We can have first tensile, which consists on stretching the material. We can have compressive stresses, which consist on squeezing the material. And the third type is shear, which will cause adjacent portions of the material to slide against each other. And for each of these types, we can draw what is called the stress-strain curve, and we will define together in this chapter what is stress and what is strain. So this is the basic relationship that will describe the mechanical properties for the three types of stresses and strain relations. We will start first by a tensile test, okay? Tensile test is one of the most common tests for studying stress-strain relationship, especially in metals. And in this test, what we do is that we put a force that will pull the material, elongating it and reducing its diameter. You will have reduction of diameter first due to conservation of volume. Okay, so length is increasing, so A will be reduced. As you can see in this figure, so here you have the initial specimen of length L0, and you are applying forces at the two ends of the specimen, which will lead to an increase in its length. At any moment, you can measure the value of the length. We will continue to do this until fracture, okay? So, whenever we want to do this test, what we do is we put gauge marks. So we put gauge marks on the specimen, and we can measure the distance, the variation of the distance between these 2 points. So this distance will vary. It will increase with time as you are doing the tensile test until it will reach a maximum value at which you will have a rupture. So we can see here the different phases of, in the next slide here, you can see the different sequences of tensile test. So this is the initial state. As you are applying a force F, you will increase the force step by step until you will have necking. What is necking? As you can see, in the first procedure, when you do the tensile test, you will have elongation and reduction of area, but the reduction of area will be uniform over the whole specimen. So as you can see here, you have same cross-sectional area over the whole specimen until you reach a certain force, which will be the maximum possible load. At this maximum load, before necking, okay, at a certain force, what you will start to observe is at a certain section, okay, you'll have a much higher reduction in area than other sections. So the reduction of area will not be any more uniform. And in this case, your critical section will be here. So this part will undergo a very fast deformation, okay, by reduction, a very fast reduction in this area, which will cause at the end, after a certain part, which is called necking part, you will have a rupture, okay? And once you have rupture, in order to determine what is the final length of the specimen, you join back the two parts of the specimen, and you can measure the length just before fracture. So this is L5, okay? Now, what is the machine that can conduct the tensile test? This is the tensile test setup. As you can see here, it's a simple machine. You have a fixed crosshead. You put the specimen between two crossheads, one fixed, one in motion. So the moving crosshead will allow to put the specimen in tension. Okay, so as you can see here, this crosshead will move downward, causing the specimen to undergo tension, and the whole system is fixed on a table, which is attached to a base and actuator, which allows the motion up and down of this crosshead. So in tensile, basically, we have downward motion of this crosshead to cause tension. You will see that in the compression case, on the opposite hand, we will have motion in order to do compression. So if we want to use this head, it will move up, or if you want to use the upper one, it should move down. Any question until here? Please stop me if you have any question. Now, what is engineering stress? Okay, the engineering stress is defined as the force per unit area, and the area we take is the initial area. This is why we say it's not a true stress, because if we want to get the true stress, we should divide the force by the actual area of the specimen. Okay, so here together we will define two types of stresses: engineering stress and true stress, and we will see what is the importance of each one. If you want, the engineering stress is directly proportional to the applied force. So when you have the curve of engineering stress, it is the curve of force variation. Okay, while the graph of true stress is the force applied over the actual area of your specimen, cross-section area of your specimen. So in this case, this will represent the true stress, while the engineering stress is mainly the representation of the force variation. Okay, so whenever you want to just see how the stress is varying, you can look at the true stress graph, while if you want to see how the force is varying, you look at the engineering stress curve. Okay, now, and we, of course, we have a relation between both. Okay, so if we say this is the engineering stress, and the definition of true stress is F over A, we can say that the engineering stress over the true stress is given by F over A0 divided by F over A. Okay, so you have that it will be equal to A over A0. Okay, so if I'm performing a tensile test, this is smaller or higher than 1 for a tensile test. No, who will tell me if you are performing a tensile test as your specimen is elongating, what's happening to the area? Yes, of course, it's reduced. Okay, so since it is reduced, then we can say that A over A0 is smaller than 1 in tensile test. Okay, so in tensile test, this ratio is smaller than 1. So we can deduce that we are drawing the curve of engineering stress versus true stress for the case of tensile test, will have that the values in engineering stress will be smaller than the values of true stress, which is the opposite in the case of compression. Because in the case of compression, what will happen? The area of the specimen, the cross-sectional area of the specimen will increase. So if you are in the case of compression, it's the opposite. And the absolute value of the engineering stress, okay, will be higher than the absolute value of the true stress. Why I am saying absolute value? Because in compression, the stress is negative, okay? But when you just name it as compression stress, so the sign, the negative sign is included in compression, so you can take the positive value. Okay. So let us continue. Now, what about engineering strain? Definition of engineering strain is the variation of length over the initial length. Okay. So the strain is at any time is the length of the specimen minus L0, which is the initial length of the specimen, over the initial length of the specimen. Okay, so this is called the elongation. Okay, and it is, we will see that it is a measure of the ductility of the material. Okay, because it will measure the capacity of the material to deform. Higher is the elongation, higher is the ability of the material to undergo deformation. Okay. Now, the typical engineering stress strain plot is given in the following figure. Okay, so if I want to represent the variation of stress, okay, sigma, so stress is F over A. Okay, now we said that we have two types. We have engineering stress and true stress. If we are in the case of plotting the variation of engineering stress, so we will plot F over A0, function of the strain E, okay, or epsilon. Sometimes this is the stress is, this is the symbol of stress. We put in general sigma engineering for the is equal to F over A0. Function of the strain in general is symbolized by epsilon. Okay. So if we look at this figure, we can distinguish two phases mainly, or three phases. You have first an elastic region in which the variation of stress with strain is linear. Okay, so you have a straight line here, and the slope of the straight line, if you find the slope of the straight line, this is the slope. The slope will represent what? Which characteristic of the material is given by the slope? Who remembers? Do you remember which coefficient is given by the slope from mechanics of materials? Yes, very good. It is the modulus of elasticity. Okay, so in this region, we have the elastic region is given, the equation is given by sigma. Okay, sigma is equal to the elasticity modulus E times epsilon. Okay, so epsilon is the strain, sigma E is the engineering stress, and E is this is the elasticity modulus. Okay, and this phase from this the linear phase here is called the elastic region. So whenever you have epsilon in this range, okay, and y and stress in this range, this is called the elastic region. The limit of the stress limiting the elastic region is called the yield strength. Okay, so this is the yield strength. Now, sometimes in some materials, this point is very clear. And you can, and if I give you this graph like this, it's clear that you have a point that will be a transition from the elastic region to the other region. So sometimes if it is clear, we directly say, no, this is a transition point and it is yield, it corresponds to the yield stress. But sometimes if you have a curve like this, for example, it will not be very obvious to determine like this, for example, okay? So if it's not, you have not a point, you don't have a point, you just have like a curvature here. It's not very simple to determine what is the yield stress. This is why we have another method to determine it, which is called the offset method, okay? The offset method consists on the following. I consider epsilon equal to 2%, okay? So for an elongation epsilon equal to 0.2%, this means if epsilon is 0.002, okay? I put it on the graph, I put the point as you can see here, and I draw a line that is parallel to the linear portion, so like this. And then it will, I say that the point, the corresponding point of intersection between this line and my curve is the yield strength. Okay, so this point here, I read the corresponding value on the axis of stress. It will give me the yield strength. Okay, so again, this method is used in general when the point is not very clear on the figure. Now, this is for the first region. This is the elastic region. After, for a stress higher than the yield stress, I have the plastic region. Okay, and what is the main difference between elastic and plastic? First, in the elastic region, the modulus of elasticity is enough to define the behavior because sigma is E times epsilon. On the other hand, in this part, it's different. It's a different equation. First, it's clear that it's not linear anymore, okay? And we will see together what is the equation of such parts, okay? How we can find its equation. Now, also in the plastic region, we have two phases. We have a phase of increase of the stress until reaching a maximum point of stress. This is the tensile strength, which is the maximum stress. And at this point, we reach the maximum load because we have seen together that the engineering stress is directly proportional to F. So the maximum of the stress here will correspond to the maximum load. Okay. Now, after this point, we say that necking will start. Okay. So this point will be the limit between before and after necking. Okay, so the plastic region can be divided into two phases: before necking and after necking. Okay, and the main difference here, why the stress will be decreased after necking? What is the physical explanation of this? Who will tell me? Why the engineering stress will be reduced when necking will start? Any idea? Look, let us go back to the figure here. Okay, when necking will start, what will happen? We will have a drastical reduction in this area. Okay, so when the area is reduced in a very fast way, okay, then you know that in order to achieve a certain deformation, because this area becomes much smaller, you will need a smaller force to continue your deformation. Okay, because before, what was happening before is that the whole section, the whole specimen is reducing area at the same rate. Okay, which make it more hard to continue the deformation. But whenever necking starts, you are just focusing on this part. Yani, since you have a high reduction of area in this part, and the rupture will mainly take, the deformation will mainly take place in this part of the specimen, then it will be easier to continue deformation. Okay, this is why after we reach the maximum load, what will happen will be restricted in a small zone, and the reduction of area will be much faster. This will cause a reduction in the force needed to continue the deformation. Okay, this explains why after necking, okay, the engineering stress, which is directly proportional to the applied force, is reduced. Okay, until at the end we will have fracture. Okay, at fracture we have the specimen is cut in two parts, and in this case, whenever reaching a certain elongation, this is called maximum epsilon. Okay, and it will help us into calculating the elongation ratio, which is L final minus L0 over L0. Okay, so this is epsilon final. Okay, epsilon final is a measure of the elongation of your specimen. So here we have epsilon final. Okay, so this is the information we can get from the stress strain graph. Now, let us continue. So here we will summarize what we concluded from the stress strain graph for engineering stress. So the relationship between stress and strain is linear in a first phase, which is the elastic phase, and the equation of stress function of strain is given by Hooke's law, where sigma E is equal to E times epsilon, where E is the modulus of elasticity. The characteristics of elastic region is that the material returns to its original length when stress is removed. Okay, so this is why we say it's elastic. So if I deform, for example, until here, then I remove the force. What will happen is that my specimen will go back to its initial state. Okay, it will be able to go back to its normal state before application of the force. On the other hand, if I reach the plastic region, okay, it will not return back to its initial state, no, okay? So it will return to a certain state with a permanent deformation. We say that if we reach the plastic region, the deformation, we will have permanent deformation. We can not get back anymore to the initial state. So these are the properties of the elastic region, and E is a measure of the inherent stiffness of the material. So it's like for the spring, the stiffness of the spring, it's very similar. If you do an analogy, for a spring, F equal K times delta L, okay? Here, it's the corresponding property in material, okay? So if you want E, higher is the opposition to deformation, okay? And the value of E will differ from material to material, and it's a property of the material. Now, what is the definition of yield point in stress strain curve? So we have seen together, as stress increases, a point in the linear relationship is finally reached when the material begins to yield. So it means when we say begins to yield, so it will do transition from elastic to plastic zone. The yield point can be identified by the change in slope at the upper end of the linear region. If you go back to the figure here, look, the slope before the yield point was equal to the elasticity modulus, while just after the yield point you have a sudden decrease in the slope. The slope is much lower. You know why? Because in the elastic region, the resistance to deformation is higher, okay? Higher is the slope, higher is the resistance to deformation. So you need to put a much higher stress to undergo a certain deformation. However, in the plastic region, it will be easier to deform. So this is why the slope will be reduced, okay? Because the slope of the curve represents, if you want, the ability of the material to resist to deformation, okay? So lower is the slope here, lower is the resistance to deformation, and easier will be the deformation of your specimen. Okay. Now, of course, after this point, you can no more do this the same analysis. You know why? Because the idea is that now in the necking part, the region that is undergoing rupture is very limited. So here, of course, in the figure, the load is decreased, but in actual case, it is much easier to deform in this form. Okay, because the specimen you are considering is a much smaller specimen, which is undergoing a very fast reduction in area. Okay. Now, if we continue, now for the yield point, as we said, can be identified by the change in slope at the upper end of the linear region, and it is a strength property of the material. Now we have several names for the yield strength. We can call it yield strength, yield stress, or elastic limit. So all of these notations are for the yield point. Now, what is happening in the plastic region? The yield point will mark the beginning of the plastic deformation. In this region, the stress-strain relationship is no longer guided by Hooke's law. So it's not anymore a linear variation. And we will see the type of equation that is used in this part. So as load is increased beyond the yield point, elongation proceeds at a much faster rate than before. So as we said, in plastic region, it's easier to deform the specimen. So this will cause the slope of the curve to change dramatically, and we will have reduction of slope until necking. In the necking, as we have seen before, it's a particular part where we need a much lower force to continue the deformation, because if you want the zone that will take the whole deformation will be the necking zone, and its area will be reduced drastically. This is why you will need a lower force to continue your deformation. Now, what about the tensile strength in the stress-strain curve? So elongation take place with a uniform reduction in cross-sectional area until just before necking, okay? And this is consistent with maintaining constant volume. Finally, the applied load will reach a maximum value, and in this case, the engineering stress, which is directly proportional to the force, will reach its maximum, and this point is called the tensile strength, also known as ultimate tensile strength. Okay, so another property that you can get from your curve is tensile strength, which is F max over A0. Now, what about ductility? Ductility of a material, okay, to plastically strain without fracture. So ductility is the ability of the material to undergo deformation. Okay, so it is a measure that it can be, if you want, ductility can be expressed in several ways. One of the most used definition is for ductility measure is the elongation, but it is not the only one, because ductility, if you want, it's not just a number, it's a qualitative property of material. It is representing its ability to plastically strain without fracture. Now, one of the possible measure will be elongation, which is defined as final length minus L0 over L0. Another measure of ductility is the area reduction. And sometimes in problems, they will tell you ductility is measured by area reduction, because also higher is the area reduction, higher is the ductility, and higher is the elongation, also higher is the ductility. So we can see quantitatively how the material is able to undergo deformation before fracture, or by measuring the elongation, or by measuring the area reduction. For example, the area reduction is measured as A0, which is the initial area of the specimen, over A, okay, over A final, divided by A0. Okay, and we will not have the same numbers. They are different numbers, but both will be a measure of ductility. Okay, so EL represents the elongation, LF is the specimen length at fracture, and L0 is the original specimen length. Now LF, as we have seen before, is measured as the distance between gauge marks after the two pieces of the specimen are put back together, as we have seen in the figure here when we describe the different phases of a tensile test. So as you can see here, after fracture, we put the two elements close to each other and we measure this distance between the ends of the two parts. Okay, this is the final length. And if you want to use the ratio, the area reduction, what we do, we measure the area here. This is A0, the initial area, cross-sectional area. We do a cut and we measure the area. While if we have to find the A final, then we measure the area at the next portion. So here, this is the area A final.
Doctor?
Yeah?
For the area reduction, ليش عملنا A0 over AF مش A0 minus
sorry, it's a typing error. It's minus, yes, of course.
Okay, thank you.
It's minus. So let me do it again. Put it again. So A reduction is equal to A0 minus A final over A0. Okay? Of course, it's the difference. So just here, I had a typing error, put minus here. Okay? So, and this is A0 in the figure, you do a cut here. So if it's, let's say, a circular cross-sectional area, they will give you the initial diameter of the specimen. So you can calculate this area, and they will give you the final diameter here. So you can calculate A final. Okay? So let us continue. Okay, now we will define true stress. So as we have seen, we have two types of stresses. We have engineering stress and true stress. For the true stress, the stress value is obtained by dividing the instantaneous. We divide the force by the instantaneous area. Okay, so sigma is F over A, where in general sigma true. To differentiate between the two, okay, we put sigma T, sigma true, and the other sigma E. Okay, so sigma represents the true stress, F is the force, and A is the actual instantaneous area resisting the load. Now, for also we have true strain, and as we have true stress, we have also true strain. How is true strain defined? You know that engineering strain is defined as L minus L0 over L0. Okay. Now, for so what we are doing, we are actually comparing to the initial length. But if we want to be more accurate at each stage, we should compare to the current length. Okay. So this is why what we do, instead of calculating in one step delta L by doing L minus L0, we consider small increment in length, so dl. So at each step, dl is divided by the current length L. And to obtain the total value, the value of epsilon, we know that to have delta L total, so we should do integration. This is why the true strain can be defined as integral, where L is varying from L0 to L, final length, of dl over F. Okay, so in this case, at each value of L, the true strain is defined as ln L over L0. And it is a more, if you want, so this is why it's called the true strain, because it is comparing the variation dl relative to the current length. Okay, so this is the value of epsilon, true strain epsilon. Okay, epsilon T. So also always to differentiate, you can put epsilon, T for true and E for engineering. Okay, so now another type of curve is the true stress strain curve. And we will do analysis, what is the difference between the true stress and the true strain curve. As a profile, it's a little bit close, okay? But we will see that in general, sometimes with engineering stress, it is not easy to determine the start of necking. Why? Because we have a lot of materials that where the maximum, the tensile strength is not very clear. And if I give you the following graph, I have first an elastic region, and then for the other part, like let's say it's like this. So here it's little bit flat. It's not easy to determine really where is the maximum. So it will not be simple to determine at which point we'll have start of necking. This is why the true stress, true strain will be much of help. Why? Because first, in the true stress curve, first we have an elastic region also. And we will see together that in the elastic part, nearly, okay, the two graphs will be very close to each other. And if I want to plot on the same graph the true stress versus and the engineering stress versus L, okay, it will be very close. Okay, this we will do it in a problem. You will see that the elastic region for both is nearly having the same points. However, in the other part, it will be much different. Okay, now we will see that true strain is smaller than engineering strain, while true stress is higher than engineering stress in tensile tests. Why? Because in tensile tests, as we have defined together before, that sigma true. So we have found together the ratio that sigma true over sigma engineering. Okay, the ratio is equal to A0 over A. Okay, is equal to A0 over A. So we deduce that the true stress is higher than engineering stress because A0 is higher than A in a tensile stress case. Okay, so in this case, we will do together some problems where we put the two graphs on the same graph, and you will see that the true stress values are higher than the engineering stress values. Okay, now if you want to compare, pay attention. If you want to compare true stress to engineering stress on the same graph, okay, you should have the same axis. So here, in general, when we plot true stress strain curve, we have here the true strain. While when we plot in the engineering curve, we have the engineering strain. So since the axis is not the same, if you want to compare, we should choose a same axis. And who will tell me what will be the axis that can be common for both? You can just represent the true stress and engineering stress function of L. If you do this, okay, if you do it function of L, which is the length of the specimen, you can compare both because they will be, you will have same coordinates along this axis for both, okay? Because in general, when you plot the engineering or true curves, they have different axes. The true strain will be smaller than the engineering strain in case of tensile tests. Okay, this is due to the definition, of course. So we will see an examples together after how we can draw the two on the same graph and how we can compare. Okay, so now in case of true stress is higher than engineering stress, while true strain is lower than engineering strain. So this is the first difference. Now, if I look at the variation, first we have the elastic region. Also, we have the yield point as transition between elastic and plastic. So we have a very high reduction in slope at yield point. So here, the slope is equal to E, and then after it will be reduced. Okay. And actually, if you want, in general, E, we don't